open up the command palette, Control-Shift-P or Command-Shift-P. I don't know what to do if you're in a browser. I'll give you another option in a second. Search for code spaces, and then rebuild container. Hit that. It's going to take a couple of minutes to rebuild your container. So that's option number 1. 75% sure that would work. Option number 2 is to go back to GitHub, hit code spaces, and then create a new code space is the other option. So basically, we changed the underlying stuff in code spaces, like the container the code spaces is running in, we changed. So you need to create a new code space in order to get Docker to work. Question? No.
You're still going to need to run the Docker pull command after you do this.
Yeah, so you need a new container. Quick aside, code spaces is running on an Azure VM. So there's a virtual machine. Then Docker is running on top of that virtual machine, giving you a container that you're executing in. Now we're going to run Docker inside of Docker in order to get a new Docker environment that is ours. So
Inception is fun.
it's turtles all the way down.
So are people able to do what Jason suggested? Can just anybody?
Yeah, either create a new code space or rebuild the container.
Sorry, I couldn't hear you.
Oh, yeah. So to create a space, so go to your GitHub repo that looks like bootcamp assignment, your username, click code spaces, and then click create code space on main.
Is everybody rebuilding or reopening their code space? All right, so what we're going to do is we're going to move forward while that's happening. All right, yeah, so we'll go back to the beginning, which is always a good place to start. And while those are rebuilding, just people maybe raise their hand or whatnot and let me know once that's starting to be done. But the way I've structured these next couple hours is the first 30 minutes or so are going to be talking through kind of the background and the basics, so we don't immediately need the code. So it's okay that this stuff is running in the background. But nonetheless, yes, if people are having problems, we want to make sure those are squared away as soon as possible, because the latter half we are going to be doing interactive code examples. So, having said all that, my name is Matt. I am a professor at the University of Wisconsin, and I'm going to be going through the unit of the boot camp, talking about running GPU models in GEM5. A couple quick disclaimers, one of which I should add, but the most urgent or pressing question I've gotten from you is, can I run NVIDIA GPUs in GEM5? The answer is no. Right now, GEM5 supports AMD GPUs. Offline, if people want, we can talk through all the minute differences between AMD GPUs and NVIDIA GPUs, but from a functionality perspective and what we're going to talk about today, the concepts are pretty similar. So just up front, if you're running GPUs in GEM5, that means you're going to be running AMD GPUs. Second thing, this GPU support focuses on what we call general purpose GPU or GPGPU support. So that means things like graphs or machine learning or financial algorithms, things like that are what we would fall under general purpose GPU, which we call it that to contrast graphics or GPU programs themselves, which are traditionally rendering triangles or doing AR, VR, or whatever you might be trying to do in, say, a programming language like OpenGL or Vulkan. So what we're going to talk about today and what Gem5 supports right now in terms of GPUs is GPGPU workloads. So things like that are in OpenCL or HIP, as we'll talk about in a little bit, and they're running on AMD GPUs. And then the last disclaimer before we get into the fun stuff, as I mentioned, I'm an assistant professor at Wisconsin. I also consult with AMD Research. AMD did not approve that legal process or anything, so these are all my personal views. Just want to make sure that everybody knows what we're dealing with up front. And there's many people who work on the GPU model. I've tried to list as many of them as I could here on the slide. Not just me working on this. I know a bunch of my students are planning on joining in on the live stream. I would encourage all of you to join the Slack and help people out if they're trying to get things up and running, since you all are some of the real experts. Okay, so let's get back then to where we were. So were people able to rebuild their code space? It still doesn't, or it didn't before you did this? Okay, so those of you, let's do a show of hands. So who was able to rebuild or reopen a code space? And now, vice versa, who is still trying to reopen their code space? Okay, so what sort of issues are those of you in that situation having? It's just still building? And is yours still? Excuse me? They're just still building? Okay. So if things are still building, that's okay. As I mentioned at the very beginning, all of these commands, with the exception of this pull command at the beginning, are going to be in the 11 GPU README file. So we will come back to it. And like I said, I'm going to spend about the next 20, 30 minutes talking about GPUs in general. So you don't need to immediately have these, but the goal is to have pulled our Docker repo and have compiled Gem5 using that Docker command in the background in the next half hour or so. Go ahead, Bobby.
I'm wondering, has anyone got this to work? The top thing like I'm just making sure there's no problem. So this is experimental.
So,
Is anyone having
by show of hands, has anyone been able to pull the Docker and then run the compilation command even if it hasn't finished yet? Okay, so about 5 people. And who, as Bobby said, is having problems pulling the repo where they've reopened their code space? All right, so we'll come around and we'll start looking at what's going on there. Okay.
It doesn't pull.
Okay, so if it's rebuilding and it's still not finding it, that means that it didn't find the updates. So can you try the second option Jason recommended, which is open VS? So I can go and show again, but so for those of you who tried option 1, which was rebuilding your code space, it seems that isn't totally working. So just as a reminder, the alternative was if you click on code, then you click on code spaces, and you click create code space on main, what that'll do is it'll open up a new environment that now has Docker support inside of it. So it seems like those of you who went with Jason's option 1, which is rebuilding the container, that's not working. Or at least only sort of working. Okay. This is how you did it? Let's take a look.
But this is, previously she did that, and now she's trying to do it again.
Let's give you a minute. Anybody having the same problem? Okay. Someone is helping. Great. Anyone else before we move forward who needs assistance getting the new code space open? Okay. So while that is running for those who are having this problem, Bobby and Arjan are coming around, so just raise your hand if you're still having that problem. Like I said, we're going to come back to this again in about 20 minutes. But we're essentially trying to get this running in the background as in prior sessions. So since that's going for most people, what I'm going to do is I'm going to move forward and start talking about GPUs, and then we'll come back to this slide in about 20 minutes. All right, so since I know not everyone in this room has used GPUs before, I wanted to start from some commonplace page. I know at least one of you in this room who's taken a class with me before may have seen some of these slides already. That's okay. I want to make sure we're all at the same place. So GPUs, or graphics processing units, came about because originally there was a killer app that couldn't run very well on CPUs and multi-core CPUs. That was graphics, or 3D games, as I know many of you throughout the week have been talking about. And so this came around in the early 2000s, where ATI, which was later bought by AMD, and NVIDIA were progressively designing these increasingly powerful accelerators to accelerate graphics. And that's where the modern GPU came about. Of course, for most of you, this revolution, as you can see from the slide here, happened in the early 2000s, maybe before you can remember some of this. The much more modern new killer app is machine learning, or depending on how crazy your favorite aunt or uncle might be, crypto. So just another disclaimer before we go further. I'm not going to teach you how to run crypto in Gem5. However, I will teach you how to run machine learning in Gem5. I will leave the crypto to the advanced expert user. But those are the kinds of algorithms that have been driving the complete scarcity and inability to purchase new GPUs in the past several years, as I know a few of you have been discussing. And so what we're going to do over the next couple hours is I'm going to first go through the basics of GPU architecture and programming. And the goal is that by the end you'll understand the basics of how AMD GPUs are implemented in Gem5. You'll be able to compile the Gem5 GPU model and understand why we use this extra Docker support that Jason referenced at the beginning. Then we're going to run some basic tests, and we're going to look at different configurations and how they impact the results for the exact same application running in that GPU model. And then we'll actually build on some of the topics from the last couple days, like M5 ops. We will add in that support to one of the applications so you can see how that impacts the behavior. And then tomorrow, Bobby will show you how you can actually check in that change to this application to the Gem5 repository in his session at that point. And at the very end, I'll point out how all those people you saw in the earlier slides and we've developed a bunch of starter resources. If you want to start doing research with GPU, to get the benefits of all the stuff we're going to discuss today without starting from today zero, we've done a lot of work to help enable that and give you resources to get up and running very quickly. Okay. Having said all that, let's talk a little bit about the basics of GPUs. And for some of you, you may have heard that there is this taxonomy in computer architecture we use called Flynn's taxonomy. And what we're going to do today is we're going to specifically focus on Flynn's taxonomy as it relates to data parallel workloads. The idea of a data parallel workload is that it's something that has identical independent computation that you're doing across multiple different data inputs. And the way Flynn's taxonomy works is it divides up the different ways that you perform instructions and access data into 4 categories. So there is MIMD, or multiple instruction, multiple data. The idea here, similar to some of the things you learned about with Parsec earlier in this week, is when we're doing completely independent work on different processes, potentially on different processors in our system. And so we'll just launch a bunch of threads. For example, the P threads that we talked about with Parsec, Each of them is going to be doing its own thing with minimal communication amongst each other, and they just work in parallel most of the time. So this works. You can get parallelism out of it, but it also means that everyone has to do everything on their own, even if some of the computation they might do might be similar. The next option here is what we call single instruction multiple data, or SIMD. And the idea of SIMD is, well, what if I have the case where an application that's running, all of those different threads or different vectors we might be using, they're actually doing the same thing. They just want different data. Well, in that case, we can actually design very optimized hardware that fetches an instruction once and then gets the data for each of the different things we want to do on it and performs them all in parallel. And so on multi-core CPUs, this has taken the form of vector extensions, things like AVX and SSE. With GPUs, we'll talk about how very similar concepts are applied there. But the key underlying idea here is that this is much more efficient. Unlike MIMD, where we have to fetch all those instructions for every thread we're running, in SIMD, we only have to fetch it once. So we get benefits out of that. Question? Or just help with the Docker? OK. And there is everybody's favorite, has their favorite cousin. With SIMD, its favorite cousin is what we call SIMT. And what SIMT stands for is single instruction multiple threads. And there's a very subtle difference here, but the key difference is on a multi-core CPU, you have one instruction and a single thread that will vectorize and perform those computations, as we talked about yesterday. In a GPU, instead of having one thread doing all that work, you have n threads that are each doing the single instruction for their corresponding piece of data. So just like SIMD, we have to fetch the instruction once. We'll do it at the same time in lockstep. But we now have multiple threads, each of which are accessing their own register file. And this is, although very subtle, the difference between what multi-core CPUs do with vectors and GPUs do with threads. Question? I will say, though, oftentimes in the community, you'll find that SIMT and SIMD are referred to interchangeably. I am going to strive very hard to talk only about SIMT today, but we can talk offline if people want about those differences. Already going through the different examples, but maybe very quick graphically, the difference between these approaches, as I mentioned with MIMD, you have a number of completely independent threads, as is shown on the left, with a vector approach, coarse thread that's accessing all this data and performing it. And then SIMT is sort of in between the two, right? We have the same number of threads maybe that we had with MIMD, but they're in lockstep like it was with SIMD. And there's pros and cons to doing each of these different approaches. In particular, what the problem is if those threads are not able to do the same thing at the same time, all of those benefits we get from fetching this instruction once and doing it for everyone, they go away. So we call this divergence. Our goal when writing GPU programs is to write it with as little divergence as possible, because divergence is going to crush your program performance and make it very difficult to get an efficient application. That all are going to be optimized differently when it comes to memory. In particular, traditionally, GPUs were optimized for streaming. And this is very different from what we've been talking about even this morning about Ruby and how we want to try to cache things, keep it heard in your architecture. All of our cache is to keep as much of the data as near as the processor in this fast memory as possible. And that is, however, with GPUs, we have thousands, maybe millions, or even billions of threads that are running simultaneously. We don't have enough cache for all of them to be occupying that fast local memory simultaneously. So instead, what they're designed to do is just accept that these accesses are going to often go to farther memories or use programmer tricks that we'll talk about in a few slides, and instead allow as many threads as possible to be performing those memory accesses at the same time, so we can hide the latency that any one of them sees with the other hundreds or thousands of memory requests that might be going on at the same time. And so hopefully your first thread, when it sent out its request and went to DRAM and came back, by the time it comes back, you'll have filled up that execution period with lots of other threads sending out to memory. And by the time the first one comes back, oh, we didn't waste too much time because we actually filled that space with useful work of asking for other threads' memory requests. But again, as it comes to things like caches, this means that we don't have a ton of reuse, so we're not going to see the same benefits that caches do in multi-core CPUs. And it also means that we can design the cores differently. We don't need all these fancy, complicated things with the O3 model that you might have heard about with multi-core CPUs that are doing out-of-order processing, because all the things like instruction-level parallelism that those devices are, exploiting, that are trying to find in your program, isn't going to work well for the kinds of programs that we're talking about here. And so really what we need here is we need independent threads that can send their requests to the memory subsystem and do that in parallel to hide the latency, which is an approach we call thread level parallelism, or really memory level parallelism in the community. Okay, enough about that. Let's start talking about what a GPU looks like. So, and I'm going to start generically, so not talking about what AMD or NVIDIA might use in terms of specific terminology, but just the idea of what a GPU is doing. So what a GPU is going to do is it's going to take many groups of those threads, for example, these little groups of 4 that we talked about a couple slides ago, and we're going to run as many of those groups as we can in parallel on the GPU at the same time. And so we're going to group, say, 2, 3, 4, some number of them together on what the GPU refers to as a core. And the reason why I call it a core in quotes, though, is because what a GPU calls a core and a CPU calls a core are very different. But there's a loose analogy here where we group those threads together for efficiency, and thus one of those little groups of 4 that I've shown here, you can sort of think of that as being like one thread that ran in those parsec workloads that we talked about earlier in the week. The one key difference here, though, is here the programmers actually have to write their code explicitly to use those threads and understand that those threads are there, whereas in workloads like parsec that we discussed already, the programmer mostly ignores that kind of thing. They can do better performance, but it's not necessary. Question?
What are the horizontal lines?
Okay, yep. So the horizontal lines are representing that, if we go back a couple slides, they are representing that in a SIMT approach, these threads are executing in lockstep. So all 4 of them are fetching the same instruction at the same time, say getting the memory that goes with those instructions at the same time, doing an add or a subtract or whatever comes next. So each horizontal having some lockstep instruction that all of them are doing at once. But so when we design a GPU, essentially what we're going to do is we're going to hierarchically start grouping these together. So we'll have a number of cores, each of which is executing one or more groups of these lockstep thread groups. And by then executing them on many different cores in parallel, that's how we're going to get lots of parallelism and thus good performance. And so here is where I will at least briefly touch on the terminology that the companies use. So if you're using CUDA, which is NVIDIA's programming language, or HIP, which is AMD's programming language, the terminology is on the left. And if you're using OpenCL, which is an open source consortium that's led by Kronos and companies like Apple, they have different terminology still. So each company kind of has their own spin on what they call these. But just to go through them, at the basic level, AMD and NVIDIA, they're going to call a single thread a thread. And then they're going to call those groups that we grouped together, those things that we're executing in lockstep that you just asked about, AMD will call that a warp. Sorry, NVIDIA will call that a warp. AMD, OpenCL will call that a wavefront. And then when we start grouping those smaller bundles of threads, those warps or those wavefronts together into a larger group, which on the previous slide I called a thread group, that in NVIDIA terminology is what they call a thread block or a CTA, and AMD and OpenCL call a work group. And then finally, when we go across all all of those cores that are running across, all of those threads groups that are running across all the cores in the GPU. NVIDIA calls that a grid. HIP also calls that a grid for a given kernel, and OpenCL calls that an ND range. So I'm going to try as best as possible to stick to this terminology, but I did want to just point out up front that different companies refer to these with different terminology. Ultimately, they mean something very similar on the back end, though, by thinking about this at a more basic level. And I covered this on the previous slide, but there's many such ways to program GPUs. NVIDIA's solution is CUDA. OpenCL I mentioned already. HIP is AMD's solution. Ultimately, though, all of these languages are extensions to C. So they put things like many threads running or C and C++. And that means if you're going to run a GPU program, if you look at it, it's going to look very, very similar to a C or C++ program, except it's going to have these data back and forth to the GPU, or that are massively parallel kernels on the GPU. And internally, they have support for all sorts of different kinds of things, depending on what your threads are trying to do. But let's then talk about, okay, we talked about this very generic, broad model. What does that actually mean in practice? Well, so if we take that and look at it in practice, what a GPU is going to look like is roughly something like what's on the right here, where each of those cores is going to become one of these smaller red boxes that have some local L1 cache, as well as some other memory, and then they have some small number, say 4 SIMT cores that are going to be responsible for those threads. And then backing them, they'll have some shared cache, maybe an L2 or an L3, and you'll go to main memory, for example, HBM after that. But the key thing to note here is with each of those SIMT cores in the GPU, we also have a local group of registers. Because remember, each thread in a SIMT model is going to be accessing its own chunk of registers. And so this is how we enable that when designing GPUs. So let's go through each of those in turn here. So the core that we're actually running the work on in a GPU is what we call a compute unit, or a CU. And NVIDIA calls that a SM. Their job is to run those thread blocks or work groups in parallel as best as possible on our given hardware. So the pictures we've talked about, we were assuming that 4 of them are executing in lockstep at a time. But in reality, it's actually many more than that, which I'll come to on the next slide. But the goal in each CU on your GPU is that each cycle you want to schedule at least one SIMT unit. Increasingly, modern NVIDIA and AMD GPUs are trying to schedule like 4 of these groups of threads maybe in a single cycle, but for simplicity for today, let's just every cycle we want to schedule at least one thing. And then those SIMT units in red that I mentioned before, ultimately their job rather, is to run the threads. And we will size the number of things that each of those cores can run based on some hardware buffers. For example, the number of instructions that we're able to execute in a SIMT unit would be governed by some size, which, for example, might be 10. That controls how many different wavefronts we're letting each of those SIMT units run in parallel or run one after another. So in AMD hardware, it takes 4 cycles to execute one wavefront. So it means we can have a pipeline where, as that instruction is proceeding through the SIMT core, we can start instructions from different wavefronts each of those cycles. We fetch or commit one wavefront per cycle. So just like a lot of the concepts we were talking about in the CPU world, we're doing sort of similar things here. We're just doing it at a much bigger scale, and we're doing it without a lot of the complexity that CPU. But one place where GPUs are much more complicated is the way that they access memory. So you might recall a couple slides ago I said with a GPU, our goal is to access all of these threads, which in that picture on the previous slide was 4. Each of them needs to access memory. So that means we need to access, say, 4 32-bit or 32-bit elements in parallel. But that actually becomes very complicated and is one of the ways that GPUs do a bunch of wild and crazy things. So for example, if I have some array, which this is very similar to the one that you'll be running in the next section, and all the GPU is doing here is it's saying each thread access A of I, where I is your thread ID, access B of I, add them together, and then put the result in the corresponding location of array C. So this is perfectly parallel, right? Every thread can get, as long as we have a big enough array, access their location of A, their location of B, add them together, and put their result into the add array. And this works well because if we envision that array in memory, that means that thread 0 is going to access, say, A of 0. Thread 1 is going to access A of 1. Thread 2 is going to access perfectly laid out in memory, right? We access the first location, A of 0, the next A of 2, and so on and so forth. And so what GPUs do is they'll add in this hardware feature that you see on the right of the slide called a coalescer. And what the coalescer does, spots these patterns. And it says, oh, why bother asking for 4 different locations, 0, A1, A2, A3, when I could just send one request, 0 through A3. So they coalesce all of those small requests into one larger request that's asking for data that's probably going to be on the same cache line anyways. Allows them to get better performance and more parallelism in the memory subsystem. So that's what we want, right? Remember, our goal is to never have divergence in a GPU. But if we do, for example, we have code on the bottom, instead of accessing A of 0, A of 1, A of 2, we're actually accessing A of thread ID times 2. That means that now we're going to access things that are further apart in memory. So it's harder to coalesce requests in this case, because here we want A of 0, A of 2, A of 4, A of 6, and so on and so forth. And it's hard to say, just bring me those without bringing the other words that are in between them. And so the goal of the hardware that AMD and NVIDIA add in is to find ways to minimize the number of requests they have to send out by aggregating them into these larger requests through the coalescer. Where we have to access these extra ones, that means we have to actually generate multiple requests to the memory subsystem, whereas in the first one we had one big request for all the threads that we wanted. Go ahead, please.
So why is sequential access easier to do than threaded access?
Yep. So I showed perhaps a relatively easy case here, but even so, let's ignore some of the, the more complicated striding patterns. In this case, my coalescer, let's say I can have 16 words on my cache line. And let's say that I'm accessing 32 words with, excuse me, with my warp or my wavefront. In the first case, I could just have one request for 32 words, one after another. In the second one, I need 2 requests that are one that brings in the first cache line and another request that brings in the next cache line, right? Just show, okay. Okay, so Bobby's going to come around and help those who are still having issues with the Docker while we wrap up this piece. Okay. And this is only 2 cache lines, but in reality, in more complicated workloads, it might be like my strided pattern is such that I'm accessing a cache line with every single thread in my warp or in my wavefront. And in that case, well, now I have lines as opposed to 1, right? So that's where the challenge comes in. If everything is perfectly contiguous, we just get one nice coalesced big request. If they're not, then now we have to start bringing in more and more cache lines, so we don't get that economy of scale as much as we do when they're contiguous.
So what I understand is the cache line has to be sequential.
We would like them to be contiguous, yes. They don't necessarily have to be sequential. For example, you could imagine that thread 0 accesses A of 4, thread 1 accesses A of 3, thread 2 accesses A of 2, so I go backwards, right? It's okay that they went backwards because they're still all accessing addresses in the same contiguous chunk. So they don't things all within one chunk. And this is where I sort of skipped over it a couple slides ago, but in GPU hardware, we actually have support for things called scatter and gather that behave exactly the way they described. Fairly going monotonically increasing, but they might also be all in the same range, and thus I just need one request for them. It's a very good question. Okay, there's a couple more slides I want to get to in this piece, and then we'll move on to use gem5. Something I wanted to point out here, though, is in real hardware, unlike groups of 4, like we talked about, AMD and NVIDIA actually are like doing 32 or 64 of them in parallel at once. And this is kind of a problem because they handle that many things coming at once. But we can't really put in, say, 32 banks on or 32 ports on an L1 cache because the program works.
It's all right if I take over 5 minutes or so to fix the bottleneck
Okay,
problem.
we're going to take a pause because for those of you who are still having issues with Docker, Bobby can help fix that.
Yes, there seems to be a very common problem with a very common solution. So thanks. Just for people who have this problem. Essentially, not all of you have got the latest version of the repo, and that means even if you rebuild the container, it won't have Docker on it. So I'm just going to literally type out the commands. And I'll just might as well just create a new slide actually, just to. I believe you want to do git. This is from memory, so I really hope I don't have any typos here. Git remote add upstream https github.com/gem5 bootcamp. Yep, gem5 bootcamp env. Okay, that's the first line. You want to fetch this upstream, so fetch the upstream. And then you want to git reset hard. This is 2 dashes. It's just this is a text editor, and upstream main. And then you want to rebuild the container after this. And I believe after you do that, you'll have the correct environment in front of you with Docker, and then you can run that build command that's in the slides.
Okay, so why don't we take 5 minutes? We'll pause here.
Yeah, I think
Bobby and I will come around and make sure anybody who's still struggling with this gets what they need. What I'm going to do before I come around is I'll copy and paste those commands to fetch, to pull the Docker onto this slide, so those of you who are at this point can at least make sure things are building.
yeah.
And then 5 minutes, we'll wrap. Stay here, or should we continue? Okay. Hand? Okay. Okay, we'll wait 2 more minutes then. Which will take a couple minutes, is I'm going to finish these last 4 slides in this unit, and then we're going to, I'll come back to this slide and leave it up while we take a break for the refreshments. Okay, so just to do a little bit of a deeper dive into that SIMT unit, which remember it was those little red boxes that I showed inside the compute units. They look functionally very similar to a wide CPU, except their goal is to be doing 1 instruction at a time. And oftentimes in modern hardware, there'll be 16 of them that are laid out. Like here at the bottom of the slide, you can see each of them has an ALU with some registers, and then if they're sending a request out to memory, they're all having this coalescing unit that we just discussed below them to send out the request. And the reason why they often do 16 of these is laying out 64 of them takes up a lot of area. So, some of them might have 32, but oftentimes what we do is, we're limited by the amount of area we're willing to devote. And instead of having all of those ALUs, we have very, very large registers. So unlike in a CPU, it's about 64 kilobytes of register state per SIMD unit, which is about 64x bigger than the equivalent space would be on a CPU. So we're devoting a lot of space to these registers because that's very important to feeding these instructions through our pipeline. We talked about coalescing already, so I'm going to skip through this. The last thing I want to reemphasize here before we start compiling in gem5 is ultimately, because GPUs are designed to embrace the fact that our caches are not going to hold on to all this data, they are what we call throughput-oriented processors. And what that means is they're designed to work on many things at a time, which is good because remember, we're running millions or billions of threads at once. And they're not going to necessarily get any one of them done quickly, but they're going to get them all done in bulk in parallel. In comparison, the CPUs that we've talked about the last 3 days, they're what we call latency-oriented. Their goal is to get that thread you're running done as fast as possible. They don't necessarily care about the other threads. They're just trying to get your one piece of work done quickly. And so again, that means that our goal here is to hide the latency of accessing the memory, to embrace it, not to, not to rely on caches to solve all of our problems. And in the case where we do need these fast latencies, GPUs have specialized memories like scratch pads and textures and read-only memories and so on that you can put certain data in to keep it close, which I'm not going to go into the details of, but I'm happy to talk to people offline. But just the last point I want to leave you with here is the reason why we need those specialized memories is that we can't rely on caches in the way that we did in CPUs. And just to drive that home, I have a comparison of a modern CPU and GPU cache here. So let's say our L1 capacity on the CPU is 64 kilobytes. The GPU's L1, maybe 32 kilobytes. But we have, say, 2 threads running per core on the CPU. So that means each of those threads gets about 32 kilobytes of space in an average case. In comparison, on the GPU, we have several thousand that are running on the same core, which means you get a whopping 12.8 bytes of space per thread. So I hope you really use that space and cherish it, right? Like it's not nearly the scale that you're getting with CPUs. You might say, okay, fine, but maybe we can just use those other caches to solve our problem. And indeed, those last level caches are bigger. We have 8 megabytes, say, in a modern CPU. If we have 8 cores, then we have 16 threads accessing it. You get a half a megabyte of space. It's pretty good. With a GPU, though, if we have, say, 60 cores that are each running those 2,500 threads, that means we have over 160,000 threads all trying to use those 4 megabytes of space. So you double, you get 25 bytes now instead of 12, but you're not getting a ton of space to hold on to your data. So that's why we need to design workloads differently for GPUs instead of CPUs. You just don't have the space to hold on to all this data. And so now, I think we'll take another 5 minutes here just to make sure people are caught up. I'll go back to these instructions in case anybody is still struggling with them. But we'll do 5 more minutes. Everybody get refreshments, stretch their legs, and so on. And Bobby and I will be around to answer any questions there might be. Go ahead. Good question. So the question was, what do you put in a GPU cache? Oftentimes, not to sound trite, but oftentimes the answer is the stuff that you don't put in any of those specialized memories. So you're going to use those specialized memories in the registers to hold on to the stuff that you absolutely need to be accessing. And then the cache kind of is everything that's left over, right? Which is the opposite of a CPU where the cache is holding the most important stuff and the rest of it goes away. So, there are ways, there's been people who've done work looking at, do I reduce the number of threads that are running and maybe I get more cache per thread to get better performance? And indeed, sometimes you can. But if you look, say, at a modern machine learning library from NVIDIA or AMD, what they're doing is they're optimizing the heck out of those specialized memories. And then If they can't fit something in there, the next thing they'll do is they'll essentially do tiling and blocking of their arrays so that they keep data in the caches only for some short period of time. And if they can't do that, then they just rely on the parallelism and you're SOL at that point. Question? Okay, help. Are there any other technical questions, or are these just questions about getting the pull commands working? Go ahead, please.
Can you help me make the connection between the task that you mentioned, like the fact that in GPU there are like less cache than CPU,
Uh-huh.
and then the fact that the memory system should be designed in a way that it's throughput oriented.
Yeah, so what that means is, since we only, so the question is, well, if I only have 25.5 bytes per thread, what do we do, right? Like, how do we deal with this? And the answer is, remember, we have hundreds of thousands of threads that are all running simultaneously. In that example I gave, it was like 160,000, right? So if I have 160,000 threads that are running, well, even if they miss, even if they go to the main memory, I have 159,999 other threads that can be doing their own work while I'm waiting for the request to come back from memory. Excuse me. So that's what we do, right? We design it around this idea that you're going to go to memory, probably. And if you are, well, I have lots of other things that can do work on their own while we're waiting.
So we need to fetch as much data as possible in one run.
Yes, we want to coalesce the request to bring as much back as we can, but we also are just relying on scale, right? Like, let's say your request takes 400 cycles, just to make up a number, to come back from memory. That means I need 399 other things to do work while I'm waiting for your request to come back. But we just talked about how each of those cores has like 2,500 things they can do at a time. So even if it takes 399 of them for your work to come back, it still came back, and I filled up all that time with useful work. And that process repeats over and over and over because I have so many things that are running. And I can usually hide the time it takes them to go to memory because I have this huge economy of scale. Okay, so you said you have a compilation problem? Shown in the upper left of the slide in gray. Here's a picture of all the different things you need to go through to run that application on gem5 in the GPU model. So we have learning libraries, we have gem libraries in orange and purple. You have the programming language HIP shown in turquoise. Underneath HIP, it has its own set of libraries, and underneath that, you have a number of other libraries implementing different pieces of the driver, some of which are in user space and some of which are in kernel space. And then and only then, after all of that, can you get to this sandy box in the bottom right, which is what's actually running in gem5. So there's a number of libraries that go into actually running a GPU application. Fortunately for you, one second, gem5 runs or models all of these, and most of this is going to be handled under the hood. But just wanted to give you a sense of, when you're writing a GPU code, there's a lot of layers of software underneath it that are needed to get to run on the GPU. Question? Yes, RockBloss is a matrix library, basically. So you're implementing gems or convolutions or whatever your favorite kind of math that we all learned in differential equations and then forgot about, right? Somebody else implemented a highly optimized, handwritten, hand-tuned version of that to run on these GPUs. And that's what RockBloss is. NVIDIA has an equivalent one called cuBloss that behaves very similarly. They're implementing like insanely optimized, matrix multiplication stuff. I remember when I was getting a lot of this to work in gem5, there was this kernel from RockBloss I couldn't get working, and it was this programmer had done this ninja level optimization to save one register, and like what they did broke the simulator until I figured out what they did and fixed it. So these libraries are very, very highly tuned. Go ahead. I'm going to come to that in the next couple slides. So the question is, how do we actually model all of this in Gem5? So let's talk about that. Just to give you an alternate view, there's many different dependencies. They interlink. If you wanted to get this all set up and running on your machine today, you would need to install all of these libraries properly with the appropriate versions and underlying software. I did all of that for you, which is what we're going to talk about next, so that hopefully none of you will ever have to do that, but it is a lot of work if that's the path you go. But his question was, what do we actually do with all of these different layers? And the short answer is Gem5 is, it can be statically or dynamically linked. I think normally I dynamically link it. And it's going to, in SE mode, it's going to run all of those different libraries except for the lowest level one, which is the Kernel Fusion Driver, or KFD, which in that picture I called Rock K. And that is where, you know, the actual like OSE, malloc-y type things are happening. But all those other levels, which are, you know, listed here, Gem5 actually simulates them faithfully. So it doesn't matter if it's statically or dynamically linked. I've never tried statically linking it. I'm trying to think, you know, why I'd want to do that. But because all of this is open source, it's not necessary to statically link it like sometimes you have to do with NVIDIA libraries to get that to happen. So does that address your question? Okay. Like I said, though, instead of getting all of that working, which, you know, is a lot of time and effort, what my students and I have done is we've created some Docker resources that properly installs all of those, you know, 75 different libraries we just discussed with the appropriate resources. With Bobby's help here, that is all now integrated into the Gem5 repo. That Docker command that we ran to pull the resources a couple slides ago pulls all of that for you. So now hopefully everybody is at the point where we can then just go ahead and use that. And so just to give you a little bit of insight into that command, there's really two key pieces. So first, the GCN GPU is telling you to grab the Docker for the Gem5 GCN or Graphics Core Next GPU model. And then version 22.0 is saying specifically the version for Gem5 22.0. And so you can imagine there's also similar images for 21.2, 21.1, and so on and so forth that support older versions of the software. So again, I'm happy to talk to you all about what's required to get all that software working, but from here on out, I'm going to assume that it's all there and it works. Go ahead, question? Okay, so let's talk about what it models currently on the tip of Gem5. So right now, it runs ROCm version 4.0, which is pretty close to the state of the art. I think they're about at 5.0 right now. We do have FS and SE mode support. We're going to focus today on SE mode because it's very well supported on the stable branch. The develop support was released as of like last week. The FS mode support was released as of last week and is on develop, but it's still very experimental. So that's why we're not going to do that in the bootcamp today. On the next slide, I'll point you, though, to where those resources are if you're interested to run that. But we also support a number of GPU models. Both AMD and NVIDIA have these terminologies that, if you haven't seen them before, it can be a little confusing. Excuse me. Specifically, let me get a drink of water. All right. Specifically in Gem5, we support two of AMD's recent GPU models, the GCN3, which stands for Graphics Core Next version 3, and its successor, the Vega ISA. Within those ISAs, there's several different variants. And I'll talk on the next couple slides about what they are, but for now, just know that those two variants are APU or dGPU. In GCN3, GFX 801 is the APU model. GFX 803 is the dGPU model. Vega, GFX 900 is the dGPU model, and 902 is the APU model, which is partially supported. I see a few of you shaking your head. I did not choose these names. There's somebody, you know, in the marketing department at AMD who did. You can take up the names with them. There's actually code words that go with each of them, like Carrizo and Fiji and Raven and so on, just to make it even more confusing. But both AMD and NVIDIA have that. But the point is, if for today, you might have seen that we compiled the GCN3 x86 model of gem5, and that means that we are specifically focusing on that GFX 801 and 803 support. If you want to run the Vega models, though, you would compile the Vega x86 GPU model and then compile your code for Vega. So that is what you would choose to do, but we're going to focus on just GCN3 and GFX 801 today. I know, Bobby and Jason have been preaching, the wonders of the standard library. The GPU model is behind the times. It does not currently support the standard library. So we're going to teach you all the old bad habits that Jason and Bobby have been trying to convince you not to do, which I think is totally in line with the guy who made the Bitcoin joke only 20 minutes ago. And Gem5 for the GPU support only has Ruby. So all that stuff Jason was telling you about this morning, that is how we model these kinds of systems. Any questions about what is or is not? Yes, go ahead. Sorry, I couldn't hear you. Okay. So the question was GFX 902, why do I say it's only partially supported? This is because that is what AMD officially said running with, say, their machine learning libraries. So if you want to run machine learning workloads, for example, GFX 902 has what they call best effort support. If you want to run like a workload that doesn't require those libraries, it should work. But the libraries themselves are not always tuned to run in an APU. So that's the issue there. And I'll explain the difference between APU and dGPU in 2 slides. Question?
I just wanted to ask, what did Vega introduce?
Great question. The question is, what are the differences between Vega and GCN3? There are like 1,000 differences, so it's not probably the best use of the time to go through it today. Vega is the generation of AMD's ISA where they introduced their equivalent of NVIDIA's tensor cores, for example. So they call them matrix core engines. So one of the big differences, sort of like NVIDIA when they went from Pascal to Volta, this would sort of be the equivalent leap for AMD GPUs. But there are many, many other differences. But for today's purposes, I'd say let's talk about that like afterwards. These are great questions. Anybody, please? Good question. Whichever one of my students are watching online, who's been working on the matrix core engine support, maybe they'll feel brave and chime in on Slack if it's working or not. As of last, it's not, but we are working on adding that support. Yeah, it's hard, adding in those kind of engines, but in terms of getting the ISA working is harder. So it's in progress, but not today, maybe is the right way to say it, but hopefully soon. Okay, so let's keep going. I mentioned I'd just briefly touch on GPUFS. So this commit on the Gem5 resources page, which you can look up, it's 58.389. It has all of the instructions on how to build and run GPU in FS mode. At least as of last night when I checked, Bobby hadn't pushed this to the resources page yet. But I know he's planning on doing one of those after this week. So that will be up and publicly available very soon. The reason why you might want to use FS mode, in addition to all the great things you've heard already about FS mode, one of the nice features of it is you can support newer versions of ROCm basically out of the box. So for example, SE mode, every time we go to a new version of ROCm, we have to update the system calls that we're modeling to properly run it, which is a bunch of effort. With FS mode, because we're actually simulating those system calls, that means we can just automatically go to newer versions. So I think we've tested FS mode with ROCm 4.2, 4.3, and 4.5. I don't remember exactly off the top of my head, but at least so far the versions we've tested have worked. So that would be another reason, if you want to be as close to the head of the state of the art of the software that's running, the FS mode provides that. And like I said, Matt P. here has provided very, very detailed instructions about how to go ahead and do all that if you're interested, but we're not going to focus on that today. Okay, so as I promised, briefly the difference between APU and dGPU. The simplest way to put it is APUs are cache coherent with the CPU. So we have a CPU and a GPU in a system, as is shown in the picture on the bottom. Each of them ultimately share an address space and can send coherence requests back and forth through that address space to one another. A discrete GPU or a dGPU can request data back and forth from one another, but they have to actually manually do so. Like the programmer would have to insert requests to say, hey, I'm going to send this data from the CPU to the GPU, and then when it's done, send it back. So the difference between them, from your perspective when you're running simulations might be small, but in terms of products, there is a big difference. I've shown a picture here of what an APU system looks like. That's what we're going to focus on today. But we do also support the discrete GPU systems if that's something you want to do research on. And just a brief side note, AMD has different terminology for their GPU caches. So everywhere you see TCP, that's an L1 data cache. Everywhere you see SQC, that's an L1 instruction cache. And everywhere you see TCC, that's an L2 cache. So conceptually, they behave the same, but the marketing folks have chosen different names for these pieces that I want to make sure I pass on. Okay. So let's actually now revisit the code and then get into the compilation of that code. So I'm not going to spend a lot of time today focusing on it, but just as Jason did this morning, I want to point out all the places you might look if you want to actually make changes to this code. So inside the source folder, there's an Arch AMD GPU folder, GPU compute, the mem protocol, and mem Ruby, which contain the GPU-specific Ruby protocols that Jason mentioned these folders having before. That is where you'll find the bulk of the code for the registers, the vector ALUs, the core, the instructions, all that fun stuff. In the configs folder, today we're going to focus on this APU se.py sample script. That is the base script for running the GPU, the APU in SE mode. There's also a GPU fs.py, which is the base script for full system mode. And that's how we're going to connect the system together, similar to that previous slide where we showed this picture of 4 GPU compute units with L1 cache and L2 cache and so on connected to a CPU. APU se.py is the one that's doing all of that work for you. Any questions about this? Go ahead, please. Where is the what located? So the discrete GPU is also located in all of these folders. The differences are maybe more subtle, like the config configures the GPU differently, but uses essentially the same scripts. The underlying code, for example, in GPU compute will do different things if you're submitting a discrete GPU request versus a coherent request. So all these folders that I'm pointing out where the APU code is, the dGPU code is also there. It's all, blended. It's all in the same place. Okay, so let me check the time. So we have about an hour and a half left. Maybe let's just see by show of hands. So how many of you want to actually know what gem5 does when you're running, like you're telling it to run something on the GPU? Or would you rather just get to the part where we actually do that running stuff and worry about the internals of how that actually works at some other time? So if you want to see it, raise hands. And if you don't want to see it, I guess we're going to, that's fine to, not sure? Okay, well, I'll go through it. There's actually, many levels of complexity here. This was actually an interview question I got asked a long time ago when I, got out of grad school. So who knows, maybe it'll be a good question for one of you someday. The way this works, though, is when the CPU wants to send some work off to the GPU, it's going to use an ioctl, which is an OS command, that essentially says, hey, GPU, here's some work that I would like you to do. Do it and tell me when you're done. And the way that that actually is implemented is that ROC-K level of software, the kernel driver, which we emulate in Timecode, is going to take that ioctyl command, and what it's going to do is a series of steps that are shown in pictorial form on the right hand of the slide. So the first thing it's going to do is it's going to take whatever work it is that we want the GPU to do, and it's going to create packets out of them. And when it creates those packets, let me switch to the laser pen here. It's going to enqueue those packets on our HSA software queue, which is a circular FIFO buffer. So whatever the current tail of that queue is, that would be where we enqueue this new packet or packets, telling the GPU whatever work that we want to do. And so when the GPU sees then that there's new work, which is going to happen via an interrupt, for those of you who've taken operating systems already, and if you haven't, let's just say that there's a signal that is sent to the GPU to tell it, hey, you got some new work, hop to it. What happens then is GPUs have these special embedded RISC microprocessors called command processors, or CPs, and their job in modern GPUs is to decode these packets that were put on the queue, figure out what work the GPU wants to do with them, so how many registers does it need, how much of the specialized resources does it need, how many work groups or threads is it running, and then it's going to start dispatching them to the actual compute units that are going to do the work. So what it will do is it'll decode this packet in its hardware queue scheduler, schedule that work by putting it on a hardware queue, which essentially is its way of saying, hey, here's some work that we're going to then want to send to the compute units to do the job. And then the dispatcher's job is to inspect those hardware queues and pick the next piece of work and start sending it off to the compute units, as shown in purple here, to do that work. So this command processor does this through something we call an HSA packet processor. HSA, as a few of you know, stands for the Heterogeneous Systems Architecture, which is an open source consortium by an AMD and Texas Instruments and and IBM and another of other companies that essentially was designing ways to express interfaces for heterogeneous systems. So this is a vestige of that time. What'll happen, we create these queues with it. It then maps that work through the hardware queue scheduler to the hardware queues, and that's then when the dispatcher will send that work off to the real GPU. And as I mentioned before, these packets contain a number of pieces of information. They contain resource requirements, so that's how many registers does this, does this kernel need? How many threads is it running? How many work groups is it running? Where's a pointer to the actual code that we're going to run on the hardware? How big is that code? All those sorts of things. So this is codifying and specifying how whatever work we're doing, here's that work, here's the resource information about it. Please go ahead and schedule it. So that is the very high level view of how we're going to actually schedule. And if you want to actually look at this stuff in the system in gem5 and see how we do these things in more detail, I've included some links here to different pieces of it, to the files that actually implement these different components. So the dispatcher, was there a question? Okay, the dispatcher is the next component. So ultimately, remember, we only have some finite number of resources or threads or whatever we can run on the GPU. And the dispatcher's job is to look at those packets that we decoded, which are shown on the right in the turquoise box, and figure out, okay, each of the work groups in this kernel wants, X registers, Y thread slots, and there's a Z of them that are trying to run. And it's going to figure out, do I actually have enough resources to run the work that it wants to do? Or are other things running right now that are taking up all those resources? If there is space, what it'll do is it'll schedule them to the compute units that are shown in gray here. And then it'll use some tables to actually track the status of everything that's in flight or pending. And how much of the work has been issued, how much of it remains, how much of it's done. and so on and so forth. And when it sees that all of the work groups from a given task have completed, it'll free those resources and then send a signal back to the CPU saying, hey, this work that you sent to me is now done. And we'll do whatever we want to do with it from there. And again, I have a few pointers in here if you want to look at the different components of how this actually works in gem5. And last but not least, before we get back to the compilation, in gem5, what we do is we model a pipeline that looks hopefully pretty similar to the relatively simple pipelines you learn about in undergrad courses. It has 5 stages: fetch, scoreboard, schedule, execute, and memory. Fetch, we're fetching whatever the next instruction that we want to execute. In the scoreboard stage, it's going to wait there until we know that the registers it needs to read or write or whatever are ready. So that's going to potentially be in there for a while until, say, something comes back from memory. When that's ready, though, we're going to start selecting a wavefront to actually run through our SIMT core and execute it on the appropriate resource. So if we're doing an add, we'll send it to the adder. If we're doing a multiply, send it to the multiplier, or whatever operations we're trying to do. And then if we're doing a memory operation, we will actually send that out to the appropriate place in the memory subsystem, including specialized memories like the local data store, which is AMD's version of a scratch pad, which will execute in the appropriate place in the memory subsystem. And so that's where Ruby comes in. Well, at this point, when we're doing the memory pipeline, you're actually sending those requests out to Ruby, and they're going to behave in the way very similar to what Jason told you about this morning. Okay, so that is a very brief version of how gem5 actually implements this work that we'd send to run on a GPU. Are there any questions about this before we get into the more interactive part of compiling and running some examples? Please. That's a great question. So the question was, here, I talked about how we have a number of these HSA software queues, and they sort of magically map to these hardware queues that I didn't specify how many of them there were. And so you were saying, well, how many software queues are there? How many hardware queues are there? Or is there a relationship between them and the actual hardware resources? Which actually are really, really good questions. I should make that an exam question next time I teach this course. The number of software queues is actually controlled by the driver. I believe the max is 64K. So that means if you're a really motivated programmer, you could write a program that has 64,000 queues in it. I don't recommend that, but you could do it if you wanted to. But under the hood, we don't have space for 64,000 hardware queues. So what we'll do is we'll time multiplex those software queues onto some smaller number of hardware queues, say like 16, 32, 64, 128, whatever the actual hardware vendor chooses to implement under the hood. But to answer the second part of your question, there is not necessarily a relationship between the number of hardware queues and the number of compute units. You could have 64 hardware queues and 4 compute units, or you could have 64 hardware queues and 256 compute units, right? So it's the number of hardware queues is kind of dictated by the vendor and how they design this. And there's one-to-one correspondence between that and the number of compute units because there's many different GPUs of all different shapes and sizes. But in general, the number of hardware queues is pretty fixed across all of those components. Does that answer your question? Other questions? Please.
So NVIDIA has the unified memory model, so would that be like closer to the APU or?
All right, I don't have enough time to rant about the differences between that. Question was, how does NVIDIA's unified virtual memory model compare to APUs and dGPUs? So the short answer is an APU is what I'm going to call a true unified memory system. So what I mean by that is if you have a single pointer, you move that pointer back and forth between the CPU and the GPU coherently. So the CPU, the GPU, either of them asks for address A. Address A goes to the CPU, to the GPU, wherever. You just ask for A. The way that unified virtual memory in NVIDIA works, I don't work there, but as I understand how it works, is they let the programmer have that same illusion, but under the hood, their driver is actually manually doing the copies to move the data back and forth. So it is, sort of letting you have something that looks like, that is a dGPU, but has the programmability like an APU would. So, there's some overheads there, but there's also some benefits to doing that in systems that are not an APU, right? So there's pros and cons there, but you can sort of think of it as a continuum where UVM is sort of halfway in APUs and dGPUs. Make sense? Okay, other questions? Mm-hmm. Yeah, this is a great question. So the question was essentially about NVIDIA's MIG, multi-instance GPU support, which allows you to run more than one process at the same time on a GPU. AMD GPUs have, I'm not going to say the same, but a similar mechanism because every company has to name it something different. They call it MX GPU instead, which is totally different, right? And there are actually some differences under the hood, but they both allow you to virtualize GPU resources and do what you're describing, right? So they allow you to run, say, processes from, work from different processes simultaneously on the same GPU. And yes, in gem5, the way that we would model that would be using the queues that we talked about. Good questions. Anybody else? Okay, so let's actually now come back to the compilation. So has everybody gotten this to successfully compile, or has anybody still need help with this? Okay. So let's take a 10-minute break then for everybody to stretch their legs, get some refreshments or whatever. But what we're going to do in the remainder of the time then is we're going to actually start running some real applications in gem5 on the model. So that's where we'll pick up in 10 minutes, and I will leave this up in case anybody needs it for compilation. Anybody not have gem5, the GCN3 x86 model compiled? From here on out, I'm going to assume it's compiled. So just checking one last time if anybody needs Bobby to come help with that. Okay. So first thing we're going to do in the GPU model is we're going to run an application called Square. Square behaves exactly as that application we talked about an hour ago does. So all Square does is each thread does A of I plus B of I and stores it in C of I. So it's ideally suited to run on a GPU because as big as the input is, if we can have that many threads, we do them all in parallel at once. So to run that, there is two choices here. I just realized I skipped a step, so let me switch to the editor here. But we actually provide you with a pre-built binary in gem5 for Square because it's one of the tests that we run on a nightly basis to make sure the GPU model is working. But to actually go through that whole process with you, I'm going to show you how to actually compile it and then run it in gem5. And again, as a few of you have pointed out, all of these commands now are in this README. So I'm assuming that all of you have done this already. That is compiled gem5. I know a couple of you pointed out that these absolute paths I put in are going to be different for each person because each of yours has the the appropriate pathing. So I'm going to quickly go and change these here. But the next thing we're going to do, once we've compiled gem5, is we're going to go to, from our root directory, we're going to go to gem5 resources /source/GPU/Square. And if you look in there, we have a CPP file, a make file, and a README. The README I will come back to in my slides a little bit later, but it has step-by-step instructions for how you would actually go and do this on your own. But since we're doing it in person, we don't need those. So what you can do, normally, if you weren't using Docker, you would just type make. But because we're doing this all in Docker, what we're going to do is we're going to take this next command, which I will walk you through in a moment, but what it's doing is it's telling the Docker to actually, by the way, is there a way to make the text bigger than this?
Control-Shift-P. So, let me keep doing that until...
It's zooming in that, not the terminal, though.
Is that a bigger terminal as well? Sorry, yeah, I don't know how to make it bigger for the terminal.
Okay. All right, I'm going to leave it here, just so you don't waste time on that. But the point is, in the README, you have this command, so you don't need to worry about going through and getting every character right from the slides. You should just be able to copy-paste that command under compiling square. And what it does is it's telling this version of the Docker that we pulled already, GPU version 22.0. It's saying in that Docker, with the appropriate settings for volume and workspace that I'm going to gloss over for now, let's go ahead and make the application. So in my case, because I didn't pull it in the background, it is downloading or pulling the Docker, so that'll take a minute. But for all of you, since you've pulled it already, you should see that it immediately ran, make, and compiled the binary. Did anybody have it not compile correctly? Okay, so while this is running for me, the next line here that says to run square, that is what we're going to do next. So this again assumes that you've compiled gem5. And what you need to do here is you need to go back to your home directory. So whatever the directory that gem5 and gem5 resources are in, we want to cd back to that directory. And now, and the reason why we want that directory is it means that the path to gem5 and the path to the binary that we're going to run are both in the same place. And because they're both subfolders of that location, our Docker can find paths to them and then actually go ahead and run them. And I'm going to switch back to my slides just because I have a few notes here. So you'll notice apuse.py, that's that base script that I mentioned before. This is what we're using in GPU SE mode to run the program. So we're saying we want to run GCN3 x86 gem5 opt, and we want it to use this apuse.py config file. So that is the first thing to note here. That's telling us to run GPU code. The next thing you might have noticed is right after apuse.py, we had this -n with the number 3. And this is because that ROCm driver stack, they actually spawn additional processes when they're running your code. And so by passing in these additional, with n, it tells the gem5 how many thread contexts it needs. So if you don't have enough thread contexts for whatever ROCm does when it's spawning the processes for your program, it would end up spinning forever and hanging because it doesn't have enough threads to run ROCm. So for this application, N3 is enough for what it's going to spawn for Square. And then the last thing is after the -c, you'll notice that we have this path from our current directory, which remember again is the directory that has gem5 and gem5 resources. And it ends up getting all the way to the Square binary that we're going to run. So hopefully all of you saw when you compiled the file that it did exactly this. Just a quick thing here, hipcc is the name of the compiler that runs to compile our HIP program. The AMD GPU target is important because whatever target you're trying to run on in gem5, you need to have compiled your code for that version. So if you try to run it and you didn't pass in the appropriate generation, what gem5 and actually what a real GPU would do as well is they'll throw an error and say, I don't have a binary generated for the target ISA that you're trying to run me on. But I've set that all up so that you don't need to worry about that today. Okay, so let's CD back here. In my case, because I'm not in mine, but I'm in Jason's setup, I actually didn't compile gem5. So I'm just going to let that run in the background. But what I'm going to do now, while that's running, is everybody please go ahead and start running this command here. One last thing that I'll mention, I don't think Jason mentioned this in the previous sections, but we also are going to use this flag, the -d flag. What -d does, Jason alluded to it earlier today, is it'll redirect your output. So instead of going to the M5 out folder, it will go to whatever the name of the folder you put after it is. So in this case, I called the output folder M5 out static. But you could also rename it foo or bob or zucchini, whatever you want it to be. It'll work just the same. But so Bobby and I will walk around now in case anybody's having a problem running Square. But Square is sized to be very small, so it should only take a minute or maybe 2 minutes at most for people to run. So I'll do a loop around after I get this set up to run. So any questions or problems getting Square to run? The program.
So do we just run both of these lines?
So now you would, go back to your home directory and then run this line.
Oh, okay.
And that'll take less than 2 minutes. Yes, there is an upper limit. I don't know, did Jason cover what the upper limit on thread contexts is? I think it's 64. Don't quote me, but I'm pretty sure that it's hard-coded in gem5. If it's over 64, it won't work. I've never seen a GPU application need more than like 5. Because it doesn't know what you're like. That's just a typo then. Else needs a hand? What's up?
Actually, it's not finding the directory.
You're not in the right directory. You need to be in the one above gem5.
Oh, okay.
So you want to be in a directory that has both gem5 and gem5 resources. Else? Has everybody seen it run to completion? Has anybody not gotten it to run to completion? Just show of hands. Okay, well, if it's running for everyone, then I'm going to move forward. So this comes to the next part where we're actually going to start comparing some things. So in the GPU model, we have, and this actually ties into one of the questions I got during the break about how accurate different pieces of the model are. So when the initial model was released, it used a register allocation policy that was called the simple policy. And what that policy said is, I'm just going to run one wavefront per compute unit at a time. The upside to this is there's very few stalls. There's very little contention. But the downside is I'm not really getting all the benefits of a GPU if I'm not letting things be overlapped and help hide, those accesses to memory that they're supposed to. So what one of my students, Gaurav Jain, did is he added in what we call a dynamic policy, which says as long as you have enough registers, we'll let you run up to the max number of wavefronts per CU, which the max here is 40, by just checking, are there enough registers for the next wavefront, the next work group that wants to run? If so, we're going to let it run. So the upside here is we get a lot more parallelism. The downside is that now you have more stalls, more memory contention, all those things that might hurt performance. So your mission, should you choose to accept it, is to run square with each of those two policies. And the reason I pointed out the -d before, remember each time we run gem5, it's going to overwrite your output directory. So make sure to use a different output directory for each of them so you have them and you can compare the output. But the other thing to note is the way that we do this is on the command line. What we do is we say ---- reg alloc policy, and then equals either dynamic or simple. So dynamic means run as many waves as you can. Simple means run one at a time. And I'll switch over to VS Code in a moment, but just show of hands, who thinks simple is going to do better? Nobody? So everybody thinks dynamic is going to win? All right, well, start running it and let's see what happens. Of course, people can probably just peek ahead in the slides and see what the answer is. But I would encourage you not to do that. Run them both. Only take a minute. And on the next slide, once people have gotten them to run, we're going to talk about how you actually parse the stats and figure out what happened here. But just to go ahead, this line 14, where it says reg alloc policy equals dynamic, is the one that you would use to actually run the code with that dynamic policy. And if you look at that line and compare it to the one above it, you should see that they're identical, right? The only change is the register allocation policy the GPU is using. Everything else is the same. Yes, and the directory. If you don't change the output directory, you will overwrite it, and you will be sad because you won't be able to compare the results. So that is, I joke about it, but that is the #1 issue I had when I started using gem5, is I would overwrite my results every time. So just always make sure your -d is set to something not equal to the previous one, and you'll be a happy person. Okay, so I'm going to take a minute here, walk around, see if anybody needs help. But if you are brave, you should start looking at the stats.txt files for each of the runs and see if you can figure out which one of them was faster. But like I said, once I finish walking around and helping people, I'll tell you how to start looking at those stats. Okay, you had your hand up? Scroll down, or?
It says here, like this one.
So that means it can't find the binary. CD to gem5 resources, source, GPU, square. Okay, and then run make there. Make sure you run make inside the Docker or it won't work. And then try what you did again. That, again, that's my Does anybody know which one is faster? Which one? The simple one? Yeah, so let's start talking about it. So there's many stats with the GPU. I realize my best efforts to paste the picture here is probably not visible in the back of the room. But the most important one, as a few of you are asking about, is shader active ticks. Shader active ticks basically says the GPU shader, or the GPU compute unit, GPU SM, whatever your favorite analogy is for it, was actually running, the program for this many ticks. So you can see, I realize the writing is small here, but it says system.cpu3. So that means the in an unfortunate use configures thing. Nodes are always called a CPU, even if there's a GPU compute unit attached to it. So CPU3 actually means one of the compute units in the system. But shader active ticks is effectively telling how long this program was running on the shader. And so what we can do then is we can look at shader active ticks for static and dynamic. And turns out dynamic is actually worse. Not very much, right? It's like 0.5% worse. The number of ticks here are really, really tiny in terms of difference. But nonetheless, I know most of you, or maybe all of you, at the beginning when we guessed which one would be better, said that dynamic would be better. And so this is an example of how the way that we do dependence tracking is not perfect, right? We've made a big strides in improving it, but it's definitely an area. You want to come up with the absolute perfect dependence tracking to handle these extra dependencies. Definitely something that's contributions are welcome. But the issue here is everything run. Letting an unconstrained amount of parallelism happen here, we basically caused a lot of memory stalls, such that we then just ended up taking all that time we spent, allowing everything to run in parallel, and just spent the whole time stalling memory instead. So there is a way to try and find a balance. So we did a study actually across a number of the micro benchmarks and benchmarks that are available for you to run. So blue is the static allocator, orange is the dynamic one, and the y-axis is the normalized speedup. So you can see that there's sometimes, especially ones that have like handwritten code that are doing, say, machine learning often, where the dynamic register allocator is way better, right? There's not very many stalls. Getting all this extra parallelism helps a lot. But there's also other cases, for example, ones doing synchronization in the middle. Might as well just run one at a time. All that extra parallelism is just causing, chaos in the memory subsystem. So we have actually patched this, since this graph. So about 40. Like we just saw with Square, it's not perfect. You know, as you run your applications, these are the kind of things to keep in mind is, you know, although an optimization might sound good in theory, it may not always give you the desired results. Please. Yeah, that's a good question. The mean, I don't know the mean, but the geometric mean is that the static one is 6% better, which is not great, right? But so like I said, we've actually patched it. Now the dynamic one is better on average, but I don't know the new geo mean. But we put a better scoreboard that handles these dependencies. But again, there's much smarter things you could do. But that some students did that as a class project in my course recently. So that is on the public gem5 though. So that is the very first application. But one of the things you might have noticed is Square is just running this one, you know, small kernel that's just adding two vectors together, putting them in another array. It's not super exciting. Real, you know, GPU applications, you know, they're really going to run many kernels or maybe multiple kernels. And unlike Square, this makes it hard to evaluate how they perform because what you would find is all of those stats, for example, shader active ticks, are going to be merged together into one giant shader active ticks value, which if I'm running 100 different kernels is not very useful because I want to know how long each of them took. And so this is where to those M5 ops that we talked about earlier in the week end up being very beneficial. So what we're going to do now is we're going to take one of the publicly available GPU applications from Pinotia, which is BC. And if you have already downloaded it or opened it, you might have seen that it already has M5 work begin. And typo on my slide. Let me fix that quick. What we're going to do, though, is we're going to add in dump reset stats between the different kernel calls in the application. So on the next slide, I will go through and talk a little bit about how to do that. But the key things I want to BC already has support for M5 ops with work begin. You don't need to worry about any of the stuff in terms of specifying, like including header files or making sure the make file has the support it needs. We've done that for you already. What you need to focus on is actually adding in the dump reset stats to each of the places that it should be. However, the one last thing I'll add here, is, which I didn't mention, or well, it's on the next slide, but this the way that we built in M5 ops supports into these on the command line when you're compiling your program, you need to specify where your gem5 repo is because 5 ops stuff is. So if you make file for now, you might see that it says like add/your/path/gem5. So you will have two choices there. And open it up so I can go through it with you. Either you can specify it on the command line, which I'll show you how to do in a moment, or the alternative is you can actually just go and modify the make file directly to specify where your where your path is. So specifically in this case, if you look in the make file, you'll see we have a sub make file called makefile.gem5fusion. And then in here, like I said, the gem5 path by default just says /path/2/gem5. So option 1 is you could paste in the path to your gem5 repo, which for each of you will be slightly different. And then option 2 is what I was just mentioning on my slides, where you can actually do that on the command line. But before we get there, in case because many of you had to refresh your environments to get through, and let me get rid of the absolute path again. Sorry about that. which is not the case. So first things first, we're going to go to gem5/util/m5, and then we're going to build our M5 ops using scans, which should look very familiar to how you did it a couple days ago. The only difference here is now we're doing it inside the Docker environment. And remember, we're doing it inside the Docker environment because it installed all of those 75 different libraries for you, so you didn't need to worry about it. But what I'm going to do now is I'm going to take a break here, just walk around, make sure everybody has gotten M5 ops to build, and then we'll progress to the actual changes to BC on the next slide. So just show hands, anybody? The M5 ops. Okay, so if people have scans, good to go then. Let's move on. So now what we're going to do is we're actually going to add in the M5 ops as appropriate to BC. Remember, what we do here is we're going to CD to the folder where BC is. So that's gem5 resources, source, GPU, Pinotia, BC. And then we're going to open up bc.cpp. Show here in the front in one moment. And like I said, the job here is to add M5 dump stats before and after each kernel. One minor thing I want to point out, though, make the runtime reasonable for the time we have today. At the very top of bc.cpp, you'll see max iters. In Gem5, normally that is set to 150 iterations. That takes several hours to run, which I don't have enough time to keep you all for, since I hear you want to go bowling instead. So what we're going to do on lines, we're going to change 150 to 2. Keep in mind what this means is that you're only getting some subset of kernels that are running. But again, it allows it so that it completes in a reasonable, given what we have here. But if you want to run the whole thing, you are welcome to. It takes about 5 hours. You're welcome to do that overnight and see how the whole thing behaves. Question? Okay. So just to get to the main event here, the way in HIP you know that a kernel is launching is every time you see a HIP launch kernel, this one, where it's running a kernel named cleanbc, this many threads in a thread block called threads, and this many thread blocks or work groups called with all the variables after it. So what we would want to do is every time we see one of these commands, you would want to put an M5 dump reset stats in the appropriate places. And so what this would do then is it resets your stats so that any stats that come in the next phase of your program must be from the GPU kernel. So it means any stuff that happened earlier, we're breaking off into its own stats file. And likewise, if we do the same thing after this kernel, that means that any stats that come after line 210 must be from something other than the kernel. So this should all look familiar to what you did with M5 work begin and work end. If you want to be very pedantic, and you might have seen this already, the way that we fully added support is we actually wrote this program so you can run it on a real GPU or in gem5 by having this gem5 fusion flag. So you can surround all this flag if you want your code to be able to run on a real GPU without having to delete them all. But that is a minor thing. We're going to surround these kernel calls with dump reset stats. And what that will allow us to do then, as I mentioned before, is it will allow us to get separate stats for each phase. And the last thing I want to point out here is on the command line, and if you don't want to change your make file and you want to just tell it on the command line what your gem5 path would be, you can see that we do that here by saying export gem5 path, and then you would set it to whatever the absolute path is to your gem5 directory here. And so then when you run make, it will know are, and you can link them in and get the desired result. So again, I'm going to pause here. There's a couple extra steps to get the input file to run, but I want to make sure people have the hang of how to add M5 ops in, because I know you guys did work begin, work end previously, so I want to make sure there's no confusion here. So I will walk making sure that, and then we'll move on to the actual running part. So 25 minutes to run in entirety, so I might just show you the answer to it, since that'll be right up to the end of when we complete. But nonetheless, I want to make sure things are clear. doesn't run anything. Like there's no shader active ticks or anything, so it would just be like memory accesses. One sec. So just for those who have added the command and got it to compile, I'm just going to move on to the next slide so they have it, but I'll keep coming around and helping. There's really like 3 things to do here. And again, I apologize that I did not use relative paths. So you're going to cd back to your home directory. Then you're going to run this wget command that will take from the gem5 resources repo a file, an input file designed to run on BC. And that is the last thing then. So the command at the bottom here will run everything similar to what we've done before. except at the very end, you'll see that it has an options option that is taking in this input file and running the program on that. And by the way, just because this file is very large, we set the memory size to be large enough to accommodate it. So again, all of these commands are in the README, so you should be able to copy them, again, just after updating the path here to be whatever your path is to these appropriate folders. But otherwise, you should be able to copy and paste this command and get BC to run. So again, I'll leave this up as I come around and help people who are getting the M5 ops working. But for those of you who have it working, go ahead and get it to start running. Yesterday when I tested it, it took 25.5 minutes to run this, very reduced version to completion. But if you guys can, or guys and girls can, go ahead and start doing that, and I'll show you a snippet before we end. But again, I'll keep coming around for now to help people with M5 ops. What's up?
So with this flux, are we looking into
So the beauty of is like kernels is it allows you to see the difference, for example, in shader active ticks across all those kernels. So for example, what you might have seen is of the 4 different kernels that are in BC, backtrack kernel, BFS kernel, clean 1D, and clean BC, those cleaning kernels, which are basically just initializing arrays to 0, they take up basically no time, right? Their shader active ticks are minuscule compared to these much larger backtrack and BFS kernels. But even more so, you can see that those kernels are varying significantly from kernel to kernel. And this is because the amount of work they're doing each time is different. So because they're doing more or less work, by putting in M5 ops, you're able to actually see the difference in behavior for each of them. And likewise, if you put in optimizations to the coherence protocol or the register allocator or any other feature, this allows you to view improvements kernel by kernel as opposed to just getting one big amalgamated dump at the end. So this is something that when Bobby tomorrow goes through the section on contributing to gem5, can definitely be contributed to gem5 resources. Like I've mentioned a couple times, there are a bunch of resources already there that my students and I have, among others, have put up. So for example, has step-by-step instructions of how to go through, make the application, make gem5, run it in gem5, and if you're interested in doing research on GPUs, I'd strongly recommend, whether you want to do machine learning, whether you want to do synchronization, whether you want to do graph analytics like BC is doing, we have a lot of resources there to help you get started up and get going so that, the worst of the pain of getting all these things up and running has been taken care of for you. So yeah, definitely avail yourself of that if that's something you're interested in. And beyond that, hopefully what you've taken from this unit is, while there are some startup costs to getting the GPU running, and we use the Docker to help with that, once you get it up and running, it should be a fairly smooth experience because all of those complications of getting the libraries and whatever installed have been handled for you. So that kind of concludes everything I wanted to say. Like I said, for those of you who are done or you just want to let running and see the results, feel free to stay. But if not, Bobby and I will keep around and checking with those who need help. But are there any questions about anything that I've covered in the last 3 hours before we adjourn? Okay, well, I will let those of you who are done go, and yeah, like I said, I'll be around to help those who are still getting the M5 ops up and running. And hope everyone has a good afternoon, and we'll, I know once Jason comes in, he'll probably have some last announcements, but we'll see everybody in a couple hours at the bowling.